the purpose of this tutorial is to show how good is the Stirling's approximation. So, Stirling approximation that we used while calculating the configurational entropy, it goes something like this. Suppose if I take a logarithm of n factorial, I am going to approximate it as n logarithm of n minus n. So, this is what the Stirling approximation is, and we said that for large n this is a very good approximation. Okay. So, we are going to do a very simple exercise now to see what is the error. Suppose n is 5, how much is the error in this approximation? N is 20, how much is the error? And n is 100, for example, how much is the error? Okay. So, we can do that. For that I am going to use octave. So, let me write, let me do a small calculation in octave. So, I am going to write a function. The function is basically a factorial function. So, let us assume that I do not give it non integers or numbers like 0. Then if you give x, then for I equal to 1 to x, so y, okay. So, I need to define function. So, I am going to first define y equal to 1, and then I am going to say for I equal to 1 to x, y is equal to y into I, and for. So, this is basically the function. So, what does it do? So, if I give 2, then it is going to go to multiply 1 into 1, and then resultant is 1, that it is going to multiply by 2. So, it will return me 2 factorial. So, if for example, if I say f of 2, it will give me 2, f of 3 is basically 6, f of 4 is 24, and so on. So, it is basically returning me the factorial, right. So, logarithm of f of 4, let us take, is 3.17. If I calculate using the approximation, which is 4 into log 4 minus 4, I get 1.54. So, this is off by about 40% maybe. So, we can actually calculate that log of f of 4 is the exact number minus 4 into log of 4 plus 4 plus 4, and I am going to divide this entire quantity by log of f of 4 to know what is the relative error, right, f of 4. So, the error is like some 51%. Now, let us do it for a number like 20. Let us see how much is the error. Okay. So, the error has dropped from 50 to 5.7%. Suppose if I do this for 100, okay. So, the error has become 0.88%. Of course, I can do for a much larger number. Let me do it for 170. Okay. So, I get an error which is like 0.49%. So, within 0.5% for a number like 170. When we are doing the Stirling approximation, we are assuming numbers which are of the order of 10 power 23. So, you can see how good this approximation is going to be. Okay. It is going to be very good approximation. Now, why stop at 170, why not check it for 10 power 23? There is a problem. The problem is factorial 170 is some number 10 power 306. If I try to calculate factorial 171, it is going to give me infinity. That is because the number is so large that for the given storage that I have, I will not be able to calculate. For as far as the machine is concerned, this number that I am getting is already an infinity. So that is the reason why we had to stop this at 170. Of course, it will be a good idea to do this calculation and plot the approximation as well as the actual function, or to plot even the error. So that we can do. So you can say for I equal to 1 to 170, because that is the limit to which we can go. Let us say x of I is nothing but f of I. Okay, so that is the factorial calculated analytically, and let me say y of I as nothing but I into log of I minus I, right. So this is y of I. So let me calculate z of I as the error percentage. So I am going to say that is x of I minus y of I whole thing divided by x of I, and I am going to multiply this number by 100. So this is my z of I, and for, so I can plot z of I. Okay. So why is it that I am not getting? Okay, I don't understand why that is. It is storing only the number, it is not clear to me. Okay. So let me write it as a script. Okay, so I am going to define the function y is equal to f of x function, and how am I going to define y is equal to 1 for I is equal to 1 to x, y is equal to y into I, and for. Okay, so this is the factorial function. So I am going to say for I is equal to 1 to 170, x of I is equal to I, and for. So let me run this and see. Okay. So f of I. So x is now stored. So now I am going to write y of I as okay. So I have to take x of I as logarithm of factorial and y of I as I into logarithm of I. I think that was a mistake I made earlier, y of I. So z of I is basically this logarithm of f of I, sorry, x of I minus y of I divided by x of I. The total thing is multiplied by 100 to make it a percentage. So plot z. So this is how the error goes, as you can see. So the error is very high, it is more than 170, 180%, and as the number increases it falls. So, somewhere around 50 we are already down to about 2%, and when we get to 150 we are already down to about 0.8% or something, and as we go to 170 we are down to 0.5%. So, this shows how good is the Stirling approximation, and we have only reached 170. So, the numbers that we are going to consider is at least 21 orders of magnitude larger than this. So, the Stirling approximation is going to be very good for such very large numbers. And if you take a look at a book like Kreyszig, there is another form of this approximation. It is also called Stirling approximation in the probability and statistics chapter that you can look at, and probably do the same exercise with that approximation also, again to see how good is this approximation as the numbers become larger and larger. Okay. Thank you.